Welcome to the ABB webcast, How Utilities Achieve Savings by Investing in the Intelligent Grid. At this time, it is my pleasure to turn the floor over to your host, Jussi Ahola. Sir, the floor is yours.
Thank you. So from my side as well, welcome to this webinar. At the moment, we have here on the line, we have 3 grid and substation automation and power distribution specialists available. Me, myself, Jussi Ahola, I'm as a market development manager at the ABB. Then we have here also the solution sales manager from ABB. Hello to everybody. And also one of our customers from PKS company from Finland, Matti Karhinen.
Hello everybody.
The contents of this webinar will be the following. The first, we are going to go through the intelligent grid, what it is, the description, and the drivers and ambitions of it. And then after that, we are going to show you the solution and the products, what we are using to make the more intelligent grid. And then we are concentrate more deeply about the results of our pilot projects, and then also the results from we can got from the real cases from our customers. And after that, at the end of the webinar, we will have the conclusion and summary portion, and then there at the webinar there is a possibility to get answers to the questions what you can send to us during the webinar. But first we start with this intelligent grid. The intelligent grid or smart grid is a common name for what we are using at the moment when we try to get the more smarter grid and a more intelligent grid. There is a few drivers which are driving this development. Here I am listing 4 of them. The first driver is that actually the market where the utilities are dealing, it's a monopoly market, and that's why there is also quite huge role of regulators all the time. So the regulator is following up the earnings and build up the new earning models for the network companies, and at the same time is following the efficiency and the power quality what the network companies supplying. Another driver is the growth of renewable energy resources. So there is a photovoltaic available nowadays, there is a wind turbine and so on. And the utilities, distribution utilities have to deal also with them. And there we are talking about the energy efficiency as well. The third driver is that we need to secure the reliable availability of electricity. And that is because the population in the world is growing all the time. And also we are in that fact that these conventional sources of primary energy is decreasing at the moment. But nevertheless, still the supporting technology is available. So the intelligent or smart devices are available. So the suppliers, we are here in the market for that reason, that we can help to build up more smarter or more intelligent grids. What is then the difference between the traditional grid and a smart grid. Beforehand, when we were dealing with this traditional grid, all this power generation was centralized, and the power flow was mainly on one directional only. And also the operations in the control center, that was based on the historical experience. So the operators, they knew when there was a fault on the network, they knew how to fix it by them knowledge and based on the experience what they had. But in the smart grid and these intelligent grids, this power generation, of course, it's still centralized, but there is now coming more distributed power sources. And that's giving some challenges. One is, for example, this multi-directional power flow. So we never know what is the situation in the network, especially during the time when there's a fault. So we don't know where the power is flowing, from which to which direction. So that's giving more challenges for the operators and for the utilities how to operate this line or this network in real time. The smart grids, actually, now it's when we're talking about the new smart grids, it's not actually any revolution, it's an evolution. So we cannot forget the existing networks what we have. We just adding more intelligence or more smarter issues to the net. So we don't demolish all the existing networks. We just add the next level and set up our networks to the next level, to the more intelligent level. And for that, ABB has a long-term experience and a knowledge about the smart grid solution backbones, and also ABB is well prepared for a future evolution. And then next we will show you the intelligent grid solution and also the products what we are using when we do these intelligent grid implementations. And Jarkko Holmlund will continue.
Okay, thank you, Jussi. So now we go to the next section in the webinar, and here we go into more of the let's say practical approach and the real equipment, intelligent equipment and intelligent nodes in the network. As a background information, we try to map down the main challenges of the utilities today, and one of the first factors that are significant is that the network efficiency has to be improved, how to use the network in a more efficient way. And a couple of noted challenges are that how to automate the existing network, as many of the network components now today are still manually controlled. There is very little measurement and information from the network. Secondly, is how to then again address this fact that Jussi mentioned about the changes in the network towards a more fragmented structure, and having more of this decentralized generation into the network and power resources. So basically, how do old infrastructure cope with new generation demand response, electric cycles, and so on? And of course, then you have the ownership perspective. How do network companies increase their performance in order to increase the value of the company to the owners, and also follow up on the regulators' instructions, and try not to have penalties due to their operational weakness and so on. And a fourth point that we have noticed also that how the utilities will deal with the demands of less resources within the company and how to manage the third-party service providers and subcontractors in all of this eco-culture. So basically limited own personnel to manage the same operations and maintenance. Okay, let's go. Following is the zone concept, which is a concept based on optimal network efficiency. Where we model the network operation and maintenance, and the idea here is to divide the network into smaller parts, manageable parts, by means of control, protection, and monitoring and online viewing from a SCADA system. And the main long-term objective for this is to develop the power distribution network in order to increase the quality of the electricity and the continuity of supply in a cost-efficient way. And by adding on intelligent components to the network, providing communications and monitoring and control, we can also then limit the effects of disturbances to smaller areas and to smaller manageable parts, which will effectively bring less consumers affected by the falls and revenues to be lost. If you look at a couple of these intelligent nodes that we can see now in the picture, circled around is recloser. That is basically adding on a protection zone to the network, meaning that if you have a fault in the network, you will not effectively trip the breaker in the substation, but trip the recloser for a downstream fault, which means that the affected parts of the network that will see the fault will be much smaller, and the critical loads will not be affected by the faults. If we go to the following one, we can then see also that by adding on remote control into the network for the pole-mounted switches and disconnectors, we can also manage the network into smaller parts by controlling the equipment in a safe way and having a real-time feedback to the control center. And by having a loop design in the network where actually you have a possibility to have a backfeed in case of a fault in the network, you can also supply the unsupplied customers much quicker in case of a fault in the network. Then, of course, in order to get this intelligence visualized and to really use it, you also need communication to these intelligent nodes. And here you have, of course, different ways of dealing with that, but that's essentially a very important enabler for the whole smart intelligent grid functionality. And last but not least is, of course, the control center, and having a centralized control center with a SCADA and distribution management system for the whole network visualization and operation. This is now a concept more for the rural networks and overhead lines, but then we also have another concept we have worked out as ABB for the city networks, where we see that the clients have, power utilities have a little bit different needs, where they're actually looking at how to optimally manage their assets in the network and monitor their distribution transformers, power flows, power quality, and so on, and to collect that information to a system level as well for the operational purpose, and also maintenance for that matter. So basically you have online monitoring, remote control, and medium voltage and low voltage measurement that you want to take from there. And then, of course, the information should be taken to a real-time connection, the SCADA DMS system, before, the zone concept, but here's a little bit more simplified schematics of the same. And here we are describing the different levels of functionality in the concept in means of automation. And you have the protection relays in the substation, and then you have a substation control system which is collecting data from the relays and doing some trending and measuring and reports. Then also you have in the network intelligent nodes where you have protection relays like in a recloser or a switch disconnector further down the line for control, fault indication and automatic sectionalizing, for example. And all of these functionalities are essential in order to reach advanced fault management in the system. And ABB can offer all the components and the products and the solutions for achieving this. And of course, ABB is a very flexible partner, and we have a very flexible offering for all the utilities for making the network more intelligent, both for the city networks and the rural networks, overhead lines. And we have, of course, the protection and control intelligent electronic devices. We also have control assemblies that are standardized and pre-tested with different kind of apparatus and switchgear. And these are, of course, tested together that they are fully operational together according to standards that are available on the market. So retrofitting is also a possibility and a good solution for this network automation solutions. Then quickly looking at the different communication alternatives, we can acknowledge that there are different kind of technologies available by terms of cost and performance, whether they are wireless or wireline type of communication. And then, of course, if the utility wants to own their own communication network or pay by cost or basically effectively by data rate. And we have seen that a couple of main trends are available, and one of them is to use the fiber optic networks in city networks. And this is, of course, very good solution, having very high capacity, allowing simultaneous services to run on the same communication network. You can utilize the modem protocols based on TCP/IP and so on. But then again, on retrofit type of solutions where you need to adapt the existing networks, wireless public communication is one of the mega trends that is in the business today. And this is, of course, very cost effective and secure if you do it in a correct way, managing the security and reliability aspects that are needed. And of course, ABB has the capability and the technology and the knowledge for also supplying this part.
Thank you, Jarkko. Then we continue to the software, because Jarkko also mentioned here that there is also a control center where all this information from the intelligent grid have to be concentrated using different kind of communication methods. We have a software for that. We call it, our product is a MicroSCADA Pro. It's a modular software, including the SCADA features, of course, so it's possible to control and supervise the breakers and switches and the whole network. And it also includes the distribution management facilities, so there is a real-time information about the network itself. Next, I will show you in practice what it means. So how this intelligent grid with the zone concept and with the software so the whole solution will work. I have an example of automatic fault isolation and power restoration, and here I will use this zone concept picture to show you how it works. So normally the operation in the control center, the control center operator, they are just sitting there waiting for what is happening. Then there happens or occurs the fault in the network. You can see in the picture this small picture with which case, which means that when there is a fault, of course this relay on the substation, it trips the whole feeder, so this green feeder will be unsupplied. And next, what will happen? Sorry, I just have to take the next picture. So the breaker trips, and then it means that this breaker or IED from the substation is communicating automatically to control center, and the software package in the control center, it locates the fault automatically. Because in the control center we have all this information about this network available, the system can analyze the switching status automatically, and it can locate the fault based on the information from the relay. Also we have a support for AMR meters, which you can see this circle. So these AMR meters, actually they are sending actively the information through the GPRS communication, or what it is, the communication way, that these households are unsupplied at the time. When the system has got all this information, it generates automatically restoration sequence, how to restore the power to the healthy part of the network automatically. So the system locates the fault, and then it sends the command to the field devices like remote control disconnectors, and it restores the power from backup power source to the healthy part of the network. And this will happen only in few seconds or a few tenths of seconds, and in this case actually we can already start to talk about self-healing network. But still we have, of course, the permanent fault on the line. System also supports the control center operator, so that the operator can follow the field crews online on the map where they are moving and where they are working. So then the operator can easily find the nearest field crew and a team who will fix the actual permanent fault from the network. And the control center operator can guide the field crew to the right place, straight to the right place, so they don't have to find out where is the location of the fault. And actually the field crew can concentrate straight to the work what they have to do. When the fault is fixed and the field crew has informed the call center that now, okay, we have fixed the fault, so the control center operator can now restore the power to the unsupplied area. And now everybody has a power supply back, so all the customers are actually happy now, but still the network is not in that position or in that state as it was before. So now the control center operator can easily operate the network so that it is in the same state as it was before. So actually he or she just send commands to the remote control disconnectors, and then first of course create a loop to the network, and then open the loop from we call normal open point. So then the network is again in the most optimal way to operate. So we save the losses and so on. So that was the short example how the system works. What is the automatic fault isolation? We called also as a self-healing network. Then we have these real cases from Finland. We have two different examples. The first example is from Fortum. Finland. Fortum is the biggest utility in Finland, and Fortum has done one pilot case in Masala substation. In Masala substation they took two feeders where they put more intelligence. Actually they're dividing this network, as you can see in the picture, to 4 different protection areas. The light blue feeder is divided to 2 portions, and then this dark blue line is divided to 2 portions as well. So the first protection zone will be from the substation up to the first recloser. And then the network is also divided to 20 different remote zones, which means that in each of the points there is a remote control disconnector, so the operator can easily and fast control the network, and also the system can automatically control the network. What was the benefits then when to do this kind of installation and this kind of pilot case? In this chart you can see 2 different charts, before and after chart. The vertical axle in these charts describes amount of unsupplied customers in percentage, and then this horizontal axle it means the minutes, how long is the outage duration. The traditional way to control the network or find out the fault and to fix the fault is so that the first it takes quite a long time to find out the fault and start to isolate that faulted part. With automation we can shorten the time first, but with these new protection zones we can actually limit the affected areas and also the customers, how much of the customers are affected by the fault. So this after chart you can see that at the beginning of the fault or outage there is only 50% or half of the consumers are unsupplied because of these protection zones and these reclosers what are installed to the network. And by this solution there was some key targets from what Fortum actually look for. And of course the first thing is that they were looking for a reliability and more better quality power. That was the key issue what they're looking. But also they had a problem because in the control center the operators they got too much information. That kind of information which was actually unnecessary for the control center operators, and they didn't have enough time to focus the tasks what they have actually to fix the faults and to restore the power. for consumers. And then also you can see in this chart the values what Fortum tried to find out to decrease the SAIFI and SAIDI values. So the system average interruption frequency index and the system average interruption duration index. So they try to decrease also these values. But what was the real benefits? Because of all this information, the whole information is stored in the DMS database. So now we have quite easy to check what are the real results. The system has installed, this pilot case was installed 2011. And now you can see the results. So actually the duration of outage was before the installation is about 49 minutes. That is the blue line in this chart. And after the use of this system, at the moment it's about 26 minutes only. And now we have to remember that now we are talking about the overhead lines. This is not the underground or this kind of city center line. This is a real rural area network. And also the frequency of outage. It was at the beginning 3.2 or 3.3 falls per customer approximately, and at the moment it's 0.4 approximately. So this is a quite dramatic change what has happened in that pilot area. Another example what we have the Pohjois-Karjalan Sähkö PKS from Finland. And now Mr. Matti Karhinen from PKS, he can first tell a little bit about the PKS company itself.
Thank you, Jussi. Pohjois-Karjalan Sähkö is the parent company of an energy group operating in eastern Finland. PKS pursues and develops a service for renewable and energy use to enable its customers to manage their energy consumptions. The group's business units accountable for business results are electricity sales, electricity generations, distribution business, and network constructions. The company's distribution network reaches 19 municipalities in the province of Northern Karelia and the province of Savo. KES electricity distribution network has a total length is 21,000 kilometers, and that 19% is overhead lines, and we have over 600 medium voltage faults in a year. The replacement of meters for automatic reading is the largest single network investment in the company's history. The cost of which will amount to more than 20 million euros.
Okay, thank you, Matti.
The group's alternate investments are 23 million euros in a year.
you, Matti. And now we are coming to this PKS case study. This intelligent grid installation or grid automation installation has done or installed to PKS network in 2009. In the left side you can see the whole medium voltage network of PKS. And now in this case study we are going to take one substation, it's called Ilomantsi, and one feeder from Ilomantsi substation called Hattuvaara. And in this investment, what PK has done, actually they dividing this Hattuvaara feeder to 3 different protection zones. We call it now South Zone, West Zone and East Zone. And that was done so that they installed 2 new reclosers to the location which are located by the arrows on the left side map. So what was the impact of this investment? On the right side with this dash line, the dash line actually describes the total amount of outages which are happening on that area yearly. So because of these protection zones, now all the fault spots which are happening in the east or west zone does not disturb the south zone anymore. So because of that, the amount of outages in these different zones has been reduced quite much. So at the moment, especially these south zone consumers, they are quite happy because they don't have so much outages anymore. Another impact or benefit is about the SAIDI and SAIFI values. On the upper chart, where it describes the duration of outage with this SAIDI value, there you can see this tendency that actually this duration is getting shorter and shorter all the time. Maybe you wonder why this Hattuvaara feeder, the total feeder SAIDI value first increased. The reason for that is that during the year 2010 and 2011 in Finland we had the really major storms which were really affecting, especially in these areas what we are talking about now. But if we just following up, if we take the year 2009 to 2012 and 2013, we can see this tendency that this duration of outage is getting shorter and shorter all the time. And also the frequency of the outages. There is much less outages, especially in the south part of this Hattuvaara feeder. Then we are coming to this point that what this everything is cost. The regulator in Finland, it follows the investments and the profits of the utilities because the business is a monopoly business. It also follow up the cost of outages. So how much the outage will cost for the consumers and also for utility. So what is the cost of outage? On the upper chart with these curves, it presents how much the duration of outage will cost in this Hattuvara feeder. This blue line describes if the outage occurs to whole feeder without any protection zones. And the vertical axle, you can see the time as well. So if there will be 24 hours outage on that feeder for one customer, so that will cost about 170,000 euros. And these values are based on the investigations or research work what has been done by the Technical University of Helsinki and Technical University of Tampere. They have asked from the utilities and also from the customers how much the outage will cost for them. And all these curves are based on these values. So with these protection zones, actually, we can decrease this outage costs quite a much. So, for example, in this case, in this Hattuvara case, if there now have a fault in, for example, in east part, it's a purple line, east part of the network, the outage cost will be now about 80,000 euros. So that's a quite big difference to that the outage will affect the whole feeder at the same time. And on the lower side of this slide, this chart, it describes the actual values, what PKS actually has saved. This dash line shows how much these outages might cost for PKS if they haven't done this investment. And actually PKS was quite lucky because they make the investment 2009. And as I already told that these years, 2010 and 2011, they were really bad for, let's say bad for utilities because of these major storms. And as you can see now, because of this intelligence in the network and about this zone concept and the grid automation, even during these bad years, the PKS in this example area saved quite a much of money, just because of the intelligence system what they had. And now Mr. Karhinen, he will tell the future plans, how they are going to improve the network in the future.
PKS makes three classes of transformation. Improvement of power grids, addition of the digital layer, which is the essence of the smart grid, business process transformation necessary to capitalize of the investments of smart technology. The storms and sustained heavy snowfalls of recent years have challenged the reliability of power distribution system, underlining the urgency of ongoing work to modernize power grid. As a forerunner in smart electricity networks, we have integrated power distribution and data systems in the comprehensive smart electricity distribution grid that provides and applies information in real time. Thanks to AMR, substation and distribution automation and MicroSCADA Pro DMS 600, our customers already enjoy access to online details of their electricity consumptions on a monthly, daily, or even hourly basis as required, with invoicing based on consumptions. A smart grid helps customers to improve the efficiency of their energy use. In the event of power outages, our network automatically isolates fault locations, directing power distribution to parts of the grid the functions normally, while customers benefit from real-time status updates via SMS, email, and online map service, and a telephone help desk. The aim for this work was to develop a system which would to automatically analyze the faults in electricity distribution networks. This kind for automatic analysis always they use to compile the fault statistics for multiple substations easily and affordably. The analysis process a listing of faults that have occurred in the electricity network. This kind of wide range analysis should help when making future investment decisions. To improve the reliability of power distribution, we are using underground lines in all new network constructions and in work to renovate older sections of the existing power grid.
Okay, thank you, Matti. And now we are coming already to this summary part. So, what was the benefit of this investment? Actually, the utility. The first thing is this automated fault handling. Because of that, now they can reduce the amount of unsupplied customers. So, first, the affected customers are less in this moment, and then also with this automated fault isolation, the duration of the outage will be shorter. So they improve the efficiency and the quality of power supply, and that means they will reduce the costs. And at the moment we can already start to talk about the self-healing networks. Another thing is that at the moment they have a possibility to manage the field crews. And again, they will save a time much, because they don't have to tell the field crew, please go and try to fix the fault. They know already where's the fault, and they can send the right person to the right place at the right time. And because of all the information what we can collect from the network, it's reported, and because of the reporting, the utility can now base the network planning also to these reports. They can also have the automatic reporting system to report the values to regulators. they can now analyze, based on the reports, they can analyze the root causes or reasons of faults, and also they can start to think about how to preactively handle the faults. So they can analyze the most faulted areas from the network, and they can make the maintenance plans, and on that way also save lots of money, because they can concentrate to the right things to do on the right time. And now we have a time for questions, what you have sent for us, and we try to answer to these questions with Jarkko Holmlund here. Jarkko will first find out some questions, what we have got.
Okay. First of all, I'd like to thank for the activity and for you to send the questions, and we will certainly answer to every one of them, but due to time limitation, we can only pick a few. And we have a question here, for example, about the case in Finland. How much did it cost to first of all do fault detection, and secondly go beyond fault detection? Here I don't exactly know what they mean, but let's say they would like to have, let's say, the fault isolation, the reclosers, and having the communication and so on. And how much extra power was sold as a result of the first part, and what is the typical frequency of faults generally for the Finnish utilities. Shall we take the second part first?
Okay, maybe we can first answer to this, how much it cost. It's quite hard to say how much it cost really in euros or in US dollars, because it has to take case by case. And then about the frequency of the outages generally in these utilities, I think so. I don't have this answer right now. I can try to find out from the databases what is the frequency. But as Mr. Matti Karhinen told about this PKS network, they have 99% of the network is overhead lines. So that means that it's also really, it's not secured from the weather point of view. So in case there's a storm, thunderstorm or strong wind or things like that, the lines they are going in the forest, of course, these lines try to be clean out so that this weather condition does not disturb. But especially during these autumn times in Finland, here is the storms, and that's affecting quite much of faults, especially reclosings and delayed reclosings.
For the cost part, maybe we can try to share some sort of estimate if we can talk to the client. But let's come back to that. We will anyway answer to these points as well.
Yes.
There was another question about the reclosers, and could they be installed without a SCADA system? And that's for sure, that works. But the idea here was to, in order when the reclosers are automated and communicating, they can also be used for the fault management. That you can also close the breaker from the SCADA, and you can also get the fault record from the recloser in order to locate the faults in a more efficient way. Of course, the recloser by itself, as a self-contained equipment, will trip the fault, but you cannot close it if you don't have the communication. You need to drive to the site, and that takes a lot of time and cost. So I hope that answered to that question. So basically, reliability will be better if you have the recloser communicating and in operation from the dispatch center. And then there was utilities electric network studies to justify this kind of investments? Is there some kind of business model or market strategy for to do offers in these long-term solutions? I think in general, I think it's difficult to answer, and in a generic way, I think this has to be studied case by case, looking at the utility situation and the network condition and the asset condition. What kind of approach would be the best way to go? But looking at the zone concept itself, if you read that material that is available, there is some guidance that what could be the approach in going forward.
Okay, then there is a question about how much reclosers we can install on one feeder, and how many protection zones can a feeder be divided using this approach. That's a quite interesting question. Of course, there should be some kind of limitations how much there is necessary to put these reclosers, or how many protection zones is good to use. But basically these locations of these reclosers, they are actually planned using this existing information from previous faults, and then also the information how much there is a load on each part of the network. So if there is a big loads on some part of the network, and that is easy to protect by this zone or by these reclosers, then it's reasonable to install a recloser to that place, or just after that place, so then that place is secured.
There was a question about does the smart grid stop at the LV meter? I think LV meter is a good point to also to take the information of the outage, because if the meters are being automatically read to the information system, you also have better chance of finding different faults in the network and different abnormal conditions in the network. But certainly there are visions and plans for different vendors to automate in the houses, and this of course is you could say a part of smart grid as well. So the smart houses are a part of smart grid certainly. So within the buildings, within the houses, that certainly is a part of it for energy power saving. It's an essential part.
Okay, the time is running and the time is limited always in the world, so if you think you didn't get the answer to your questions yet, we have your email addresses, and we try to answer to your questions by email as soon as possible. But now we're going to end this webinar. But before ending, I would like to thank you from ABB point of view that you joined to this webinar, and I hope that this was fruitful for you and helps you. And I also would like to welcome you, if you have a possibility, to meet us in the European Utility Week in Amsterdam, 15th to 17th of October. And in the event, you can find out the ABB stand, and that will be C06. So I hope we will see each other there again. Thank you, everybody, for this webinar.